Welcome back, everybody. So we will start our afternoon session with Bernd Noack. So without further ado, Bernd, why don't you go ahead and get started?
Thank you, Mike. I assume you can hear me. So first, I want to thank the organizers for this honorable invitation to the distinguished list of speakers. Second, I want to apologize that I cannot come. I'm not afraid of the English food, but on my return to China, I would be subjected to a 3 weeks quarantine, which would be rather disruptive with my other plans. So I decided to stay here in China. Today, I will talk about some machine learning methods for wall turbulence drag reduction, in particular for about optimizing distributed actuation and reduced order modeling. This is joint work with Songxi Li, Jiajiang Luo, Cornejo Maceda, and Nangao. So they did the experiments I will be reporting about. Marian Albers and Wolfgang Schröder did the simulations, and reduced order modeling has been done together with Daniel Fernex and Richard Seemann. We have been supported by Shenzhen government, Guangdong province, and the Chinese, German, and French Science Foundation. So first, I will bring some owls to antenna and make the case for distributed actuation and sensing and the need for AI control. Then I will show one example of optimization of skin friction drag reduction with a large eddy simulation. Then some reduced order modeling for the same data before continuing with a smart skin separation control experiment using some gradient-enriched machine learning control. Then I conclude with a summary and an outlook. Most of our research projects are related to transport vehicles. At significant speeds, you always have to overcome aerodynamic drag. Part of the drag comes from skin friction, other part from a separation. Here, if you take the train, then these parts would require some reduction of the skin friction, and this part here leads to separation, which needs to be controlled for further drag reduction. Of course, there are many other transport vehicles and many other engineering examples where you need some separation control and some skin friction control. I've shown a couple of them here. So first, I talk about skin friction drag reduction in a prototypic turbulent boundary layer. Reynolds number is 1000. The turbulent boundary layer is subjected to a transverse traveling surface wave, and the analysis domain has these dimensions, so up to 100 boundary layer thicknesses large. So in the span-wise domain, we have periodic boundary conditions. The actuation for skin friction reduction is done with traveling surface waves, so similar to what Ivan was reporting, but this is in the transverse direction. These traveling waves have 3 parameters: a period, a wavelength, and an amplitude. The parameter range of the simulations is shown here. So we go about 1000 plus units corresponds to about 1 boundary layer thickness. So the dimensions are rather large. Some of these parameters give rise to increased drag, some of these reduced drag. And one is an example of the unforced flow. Here you see the isosurfaces of a lambda-2 color-coded with a u velocity. The case 24 corresponds to a large wavelength and drag reduction. This high wave number case corresponds to a drag increase. So this gives you some idea about structures. And our project started with 71 simulations where we can know the amplitude, period, and wave number and the corresponding drag reduction. You see the corresponding data here in this box. So lambda, so the wavelength, the period, and the amplitude, color-coded with a drag reduction. So here we achieve up to 26% drag reduction. So the obvious question is, where should we do our next simulation to get better drag reduction? And first we do some interpolation. This is harder than it sounds, but we did it with some support vector regression. The next thing is simplification comes from observing that for every spanwise wave number, there's one amplitude and one period where we achieve maximum drag reduction. These maxima are a function of this wavelength, and they define a ridge line. So here you see the ridge line, amplitude, wave number, period. So along this line here, the drag is minimized. And secondly, we observe some self-similarity. So if we know the amplitude and period in one plane for one lambda, and if we know the optimal drag reduction for another lambda, then we know what happens in the whole domain. So this has been confirmed for all lambda plus larger than 100. And now, in order to find better values, we extrapolate this ridge line. That means we go out of the domain which we have measured, and we predict a period and an amplitude at lambda plus equals 5,000. We predict 31% drag reduction, and this has been found in a large eddy simulation with a promille error. So this is an example of a successful extrapolation, which is rather challenging. Now we take a look at large eddy simulation data. And most of you will be aware with PUD Gajokin modeling. This is pretty challenging for this broadband turbulence flow. So we use an alternative approach, which turns out to be much more robust, cluster-based network modeling. The procedure is as follows. First, we collect the data. Here you see the states exemplified for the Lorentz equation. And after enough data, you coarse grain the data into centroids. So the centroids describes snapshot data in a certain region. Here you see the corresponding centroids. And in the next step, we look at the transition properties. For instance, if you start at cluster 1, you may go to cluster 2. If you are at cluster 2, you may either go to cluster 5 or you may go close to cluster 3. And these transitions have a probability which can be inferred from the data. And there's also an average typical transition time. So we know the probability and transition time. And with this data, we have a deterministic stochastic model with which we can build propagation. So here you see the most simple example for the Lorentz equation. How would this look like for the turbulent boundary layer? Here we see the LES data in the analysis regime. You clearly see a traveling wave and a propagation of the structures in streamwise direction. We now cluster this in 10 different centroids, so it's a rather coarse resolution to exemplify the approach. Here you see one centroid. This is a V component. Centroid 2, centroid 4. And this essentially shows how the boundary deformation commands the actuation response in the fluid flow. And this is the result of the corresponding cluster-based network model. A1, A2, A3 are the POD mode coefficients. And you see that we can capture the periodic signature from the actuation, but also some cycle-to-cycle variation. We applied this for many different actuation cases. We can also extrapolate for that, but I just want to give you a taste of the model. We have applied the same model not only to the turbulent boundary layer, but also to the Kolmogorov flow with sparse events, to medical data, nonlinear dynamics, and so on. So with one approach, we can approximate the autocorrelation function and get the characteristics of the time series. Now we go to an experiment, to our smart skin separation control. The idea is the following. Here we have a airfoil, and the dashed line corresponds to separation. If we would actuate significantly upstream of the separation line, we would lose authority. If we would actuate significantly downstream of it in the dead water region, we would also lose authority. So somehow we need to actuate close to the separation line. That means we need some type of distributed actuation. So here you see a number of actuators for the separation control, and also a number of sensors. And with the right control logic, we can reattach the flow. And of course, this can also be applied for the train. So here you see the corresponding smart skin implementation to reattach the flow. The main idea is the following. There is a two-dimensional array of actuators. The actuators may be in a sleeping mode. That means maybe fully retracted. These two lines correspond to a skin friction sensor, which we still want to implement. The actuator can turn up in a passive mode. So at this point, we have a vortex generator. And we can also blow in streamwise direction. This way we have active control, and the active control can be commanded also in feedback. So at the end, we have something like of the order of 100 sensor signals, 100 actuators, and now we need to find a control logic, and the control logic is done with some type of artificial intelligence algorithm. Here you see the corresponding implementation. We do this in a small wind tunnel, which you can see in the background here. So this is an open wind tunnel, velocity of 5 meters per second, a step height of 5 centimeters. The Reynolds number is about 33,000. So we have turbulent inflow conditions. And the control is done with 5 times 6 actuators, 5 actuators in streamwise direction and 6 actuators in spanwise direction. Here you see a triangle. The triangle can be fully retracted or can be moved out. And when it is moved out, then we can eject a microjet in streamwise direction. This can have a velocity around up to 15 or 20 meters per second. Our cost function is effectively the pressure recovery, penalized by some estimate of the energy input. The sensors are some pressure taps, 8 times 7 pressure taps. So now we have 56 sensor signal and 30 geometry parameter and 30 controllers. For this, we need to find the control law. This is a rather challenging task. Even if you would believe in a linear control, you need something like thousands of parameters which you would need to tune. This is done with some machine learning approach. So we test a controller, then we measure the performance, test another controller, measure the performance, and so on. And the algorithm for this optimization is linear genetic programming. Linear genetic programming, we start with initially something like 100 random controllers, which we test in the experiment. And from there on, we take the best controller, put it in the next generation, and we randomly select here other controllers, perform some genetic programming operation to generate new controllers. So one operation is called crossover. This tends to breed better individuals, better controllers. One is mutation, which is to explore better minima, and one is replication, just as a memory effect. And this is done again and again until we eventually stop, typically after 10 generations. So this linear genetic programming can be done, can solve this problem, but the learning process can be significantly accelerated with a new trick, which is subplex gradient descent. So what we are doing is we do a Monte Carlo initialization of the controller. Then we do some genetic programming steps. And thereafter, we take the best individuals, the best controllers, and optimize linear combinations of these best controllers with the downhill simplex methods. And this is done in several cycles. So genetic programming, downhill simplex to the best minima, and so on until we stop. And this can speed up the learning process roughly by 1 order of magnitude, as we have found in a number of different experiments and simulations. Here you see the corresponding results on the y-axis. This is the cost function. The more negative, the better it is. This is a number of experiments. You see we have 1,000 experiments, 20 seconds each. So you see that initially we learn rather fast. So the first 50 examples are random controllers, and then we do some genetic operations, some 50 simplex operations, genetic operations, and so on. And you see we stay on a plateau, and occasionally we go down until we finally reach the best individuals. The result of the corresponding best actuation is shown here. You see that only the upper actuators are active. These are the equivalent duty cycles. So this 100% means continuous blowing. 35% means it roughly blows 35% of the time. And the downstream actuators are not active. So this has been found after 1,000 experiments. If we run the same experiments with some lower velocity, then more actuators will become active, and then we also have some unsteady feedback phenomenon. Here we see the corresponding flows. This is the unforced flow of a time averaged PIV. The U component is color coded. You see this recirculation zone. The fluctuations are subjected to a POD analysis. The first mode roughly corresponds to a breathing, so to a variation of this recirculation zones. Mode number 2 and mode number 3 correspond to Kelvin-Helmholtz structures. At the moment when we control, we see that the flow reattaches, and the corresponding POD modes are centered close to the wall. Here we see some high frequency signature of some of the actuators. So we have achieved the goal of a reattachment and the corresponding pressure recovery. And this now brings me to the conclusion. So as we all know, turbulence control is strongly nonlinear, which makes it a big challenge for the first principal approaches.
So,
That
Bernd,
means for using the Navier-Stokes equation, particularly when you have, yes?
you have 5 minutes, so you
Okay,
can
thank
go
you.
slowly through your conclusions if you want.
Good. So we have strongly, the turbulence control is always based on some strongly nonlinear actuation effect. This also means that if you actuate with one frequency, you have you change a continuum of other frequencies. So linear models would generally not work, and model-based control is very challenged. I've shown one example how we can do the skin friction reduction nevertheless with a kind of brute force approach. Namely, we built a response model for the measured performance of some actuation parameters. In the example which I presented, the topology had a very important effect. So the ridge line has allowed us to extrapolate the data out of the data regime and go from a narrow wave number regime to a much higher wavelength and predict the drag reduction correctly. I've also shown that there's a robust method for doing some dynamic reduced order modeling for the broadband turbulent flows, cluster-based network models. And then I've shown you some preliminary results for our smart skin separation control, where we had to learn feedback controller with 30 geometry parameters for the vortex generators, 30 feedback laws for the mini jets, and 58 pressure sensors for the feedback. And this has been done in a couple of hours. What these examples show that machine learning can be a very powerful tool for not only for control, but also for modeling and analysis of the flow. In the traditional approach, you would first try to understand the flow. After you understand it, you would analyze it. The analysis would suggest some type of models, and the models need to incorporate the control. And then you would calibrate the found control laws with the modeling and tune the parameters in the experiment. Machine learning suggests a new paradigm, and this suggests first try to find the optimal control, try to find the optimal actuation mechanisms. Afterwards, you can model this optimal actuation mechanisms. Then you can analyze the performances, the data, the flow structures, and so on. And this analysis at the end leads to some understanding. And this is a much quicker path, and it also leads to better results. And since I have 1 or 2 minutes left, I want to use my final 1 or 2 minutes. So, okay, 1 minute. So we have a couple of positions, roughly 10 professorships still here at HIT. And we are looking for professors at all levels and also for postdocs. So if one of you is interested in joining us, please contact me, and please contact me soon. Then thank you for your attention.
Thanks very much, Bernd. Okay, we do have a couple minutes for questions. Okay, Dwight.
Thanks very much for that talk. Can we go back to the boundary layer? I didn't, the wall turbulence, I didn't understand. Yeah, no, forward. I mean, backwards, later in the talk, the cluster analysis, your cluster-based model, yes. More. Yeah, no, Laurent, I understand that. Okay, now I didn't understand what we're seeing. I didn't understand where are your clusters in that picture, and where's the dynamics in that picture? I don't understand. I missed that.
No, thank you for the question. So you know POD analysis. So in POD analysis, you would build a mode from the complete data field here. So we do something similar. We look at various snapshots, and then we average over groups of snapshots. So these centroids essentially correspond to a complete flow field in the whole domain. And what we see is not surprising. The centroids roughly correspond to the actuation response. It's roughly like phase-based clustering. And here you see the POD mode coefficients, A1, A2, A3. And every point here corresponds to one of these centroids. And when I click here, that means we go from this cluster to this cluster, to this cluster, and so on. And the transition here is predicted by our cluster-based network model. And there's a characteristic time, there's a probability. For instance, when you are here, you always go to this cluster, but when you are here, you can go to that cluster or you can go to that cluster. So there's a probability structure and there are typical transition times.
Okay, thank you. Is there?
Okay, time for one more question before we move. Okay.
You know, you put on the smart skin control vortex generator with span-wise and stream-wise. How would you how explain the fact that one are better than the others? Next.
First of all, I don't want to make a claim.
Go to the next slide.
Yes.
No.
No, you probably mean this.
Why is the vortex generator will produce span-wise perturbation, stream-wise perturbation one better
so
than
we're talking about separation control now.
Yes, in separation control. The next one. Next.
Yes.
Next. Yeah, exactly. No, previous one. This what exactly this at right. Okay, the optimized actuation. How you decided it is better span-wise or stream-wise actuators? This is my question.
So this has been we optimize the height of the actuators, and we have feedback laws where we can, for instance, command the jet independently of the pressures which we measure in the whole field. And this has been done by some machine learning approach. Essentially, we go through a large space of possible functions where we take all the sensor data and feed it back to the geometric parameters and to the actuation parameters. And these are the results which have been found. So it could be the global optimum. So we don't decide it, but it's decided by the machine learning algorithm because we are monitoring the cost, and the cost is a pressure recovery. So we solve a rather complex regression problem. So learning a controller with, in this case, roughly 60 inputs and 60 outputs is quite a challenge, but this can be done with a combination of genetic programming and gradient search. It's like solving a variational problem.
Let's thank Bernd once more for a very interesting talk.